Alright, in today's video I'm going to show you how I managed to print this benchy from stainless steel. I'm also going to show you how you can make your own welding camera and what parts are required. I'm going to explain how this contraption works. And finally, I'm going to explain where I've been for the last nearly 2 years. Those of you who have been around long enough to know what this thing is may remember that I'd given up on laser powder bed fusion as a desktop metal 3D printer. And while it had yielded something, really it had fallen short. So over the next 12 months, I took another swing at things, and well, here's what became of it. So, I think to better understand the direction things took after the last video, we need to recognise the problem I was trying to solve. Without being able to feed the wire into the weld pool unimpeded by reflections, there was no chance of this succeeding. This was something the previous design struggled with, and as a result I spent many hours terminating fibres and untangling wires. On top of this, the beams didn't align nicely, the gas flow was unbalanced, and without being able to see the weld pool there wasn't much chance of a control loop. So I hit the drawing board. The next iteration of design would play on the last, letting each beam bounce off the positive displacement created by the weld pool. To ensure that the beams were symmetric this time around, I repurposed 3 optical mounts mating each of them to a lens host, which would also serve to direct the flow of gas. The hosts themselves were 3D printed from stainless steel, courtesy of JLC 3DP. Unfortunately, they don't offer aluminium as part of their printing service, and the geometry was a little too awkward for milling. Other than the threads needing to be tidied up, the dimensions were good and the surface finish was acceptable. Interestingly, JLC 3DP quoted the density of their 316 stainless steel as 7.8 grams per cubic centimetre, making one of the parts 100% dense and another 103% dense. I'll leave you to infer what's going on there. The second major aspect of this design was to integrate closed-loop feedback. If I could achieve this, I would have a much better chance of avoiding the effects of stress and the potential need for simulation software. The only method I really deemed worthwhile was to exploit visual feedback, making an inference about the accumulation of heat based on the level of incandescent light and the size of the weld pool. With this information, I could map and dynamically adjust the energy input in real time. There was one problem, however: welding cameras are expensive. So I would need to make my own. Fortunately, in principle they are pretty simple. It really just comes down to balancing the background lighting with the foreground. Given this is a laser welding process, it doesn't generate nearly as much light as its electric counterpart, with the exception of the laser itself, which can be handled with a shortwave filter. Now I wish I could say that this was my plan from the beginning, but I went down a few roads before getting here. The first of which was informed by some older research which focused on the use of a narrowband filter alongside some pulsed laser diodes. This technique is better suited to electric arc processors as it emphasises broadband light rejection, but not knowing what else is possible, I still gave it a go. My first attempt would be a swing and a miss, as I wanted to repurpose a smartphone. I had observed my old S9 doing pretty well on more demanding circumstances, so I was pretty confident I could achieve something. But I chose to sacrifice this S6 to begin with, just to see if the hardware would play ball. The overall plan was to remotely mount the camera and remove the battery, later upgrading the phone once I was more certain of things. Things would only go south from here as the phone kept boot looping, the camera was stuck at its maximum focal length, and then I would break the screen. Meanwhile, I was working on building a pulse driver for a 50W 905nm diode. These are typically used in LiDAR applications, with some diodes reaching as high as 400 watts. Unfortunately, their wavelength was uncomfortably close to that of the lasers driving the welding process, making their performance very much dependent on the roll-off of the narrowband filters. Of course, the 2 narrowband filters I ordered arrived unmarked and had curiously similar performance, which didn't bode well as there should have been at least a 30% difference between the two. To make matters worse, I had ordered different diodes to those used in the research paper, and couldn't get anywhere near the fraction of power at 1 microsecond. Things were not going well. About a month into this and having no camera or light source to show for it, I had to stop and reappraise things. For the sake of the camera, I opted to take a less intrusive approach, trading pixel density for practicality and making up for it where I could. I also toyed with a few ideas for a light source, the first of which involved adding another 915nm pump. But this was a bit expensive and didn't allow me to juxtapose the different wavelengths, and still left me with a monochromatic image. I also really wanted a colour image, as I knew this would make processing the stream a lot easier, so I kept experimenting. I particularly wanted to try and avoid using broadly spaced laser wavelengths, so this cob LED rated at 5K lumens had its moment. I would adapt the same pulse circuit from before to overdrive the LED, but nothing really became of it, the intensity was still too low. I think some form of reflective light guide might have stood a chance, but using a lens was a mistake as the light was too dispersed, and the whole thing locked me into a weird configuration. In the end, I would concede and try using a simple 450nm 5W diode, and this is where things would finally come together. I would opt for a pulse scheme here as well, as the head needed to go on a diet, and adding a heatsink definitely wouldn't have helped. So things would continue in this fashion for a while, with the phone eventually being upgraded to an S20. I really wanted to bring the camera in closer to help improve the resolution, but as the S20 came with various camera modules, I would end up with the wrong cables and just couldn't find what I needed. You can see the image had improved slightly, but it was still too grainy and prone to being blown out in the region of interest. I just had to accept that without being able to mount the camera remotely, I wasn't going to get the image quality I wanted, and therefore would upgrade the camera to a standalone unit, this one claiming to have 78 decibels of dynamic range. Unfortunately, switching over to a standalone camera would call for a PC, adding anywhere between $500 to $1,000 based on second-hand components. Now that I had a new camera, this called for a new head, and now that I was paying for it, was made from aluminium. The camera was also paired with a 150x microscope, all very typical of PCB inspection hardware. I was also tired of having to manually synchronize the laser to the frame rate of the camera, and without wanting to add more bulk, decided to integrate a fiber. This particular fiber is much too large at 600 micrometers, but being unsure of how tightly I could concentrate the beam, decided to play it safe. This would pretty much be the configuration I would run with for the remainder of my time working on this concept, with the beam switching between collimated and focused depending on what approach I was taking. To summarize, to build this welding camera you'll need a camera with a decent dynamic range and the ability to handle low light conditions. You'll also need neutral density filters in the order of 0.1 to 0.3%. I would recommend getting a few of a couple of orders of magnitude higher, just to allow for some adjustment. If you plan to record a laser welding process, then selecting a shortwave filter with a 3 decibel point at least 200 nanometers below the laser wavelength is ideal, more so if you want to factor out the laser completely. For those more interested in recording an electric arc process, this particular camera seems to do okay without any light assistance. But for those wanting to replicate a more professional system, I've read that at least 200 to 300 watts of pulsed laser light is needed, synchronized to a camera with a global shutter, and outside of a peak within the emission spectra. I'll leave more information in the description. Alright, so we need to rewind a little bit. To get the head set up, each collimator had to be adjusted to ensure each spot was focused as tightly as it could be. For this, I used a camera from Imaging Source along with their free software tool IC Measure, and when combined with a neutral density filter would allow me to see the image projected by the light source alongside the degree of light spill. You can see from a few of these images the imbalance in delivered light, and unfortunately the cause wasn't immediately apparent to me. I'd assumed that at least one of the two lenses wasn't centered correctly, and despite repeatedly trying to realign the pair, would be forced to correct for it using whatever means I could. But later I would realise that the issue had nothing to do with the lenses and instead was caused by the SMA 905 adapter plates. Even though they are threaded, they often wouldn't sit flush despite appearing otherwise, owing to perhaps half a millimeter of play. So if you happen to notice scalpel blades hanging off this from time to time, yep. With each lens hosed aligned, they still needed to be aligned relative to each other, with each beam focused just outside their focal length and past the center point to cause the beams to deflect rather than reflect. Beyond the more mundane aspects of preparing the head for its initial runs, the first few tests really just sought to identify what was possible at a glance. With an overhead camera it seemed that this ruled out a coaxial feed, but I would try my hand at it anyway, using a J-type coupling. I had reverted to using the smaller lasers from my previous attempt at this, as I really wanted to keep costs to a minimum. Unfortunately I found that I couldn't achieve much separation between the beams at this power level, and would have to resort to more familiar tactics. As a result, the results themselves were a mix, revealing that reflections were still very much a problem, setting the tone for the rest of my time working on this concept. I would also try mounting the wire feed at a more conventional angle, yielding pretty much the same. Some trials worked and others didn't, but what was clear is that the power would need to increase to facilitate the offset beams. This would see the three 200 watt modules returning, bumping the power back up to 570 watts. Even with the power increased and despite my first run at things not really representing the planned approach, I wasn't left feeling particularly confident about relying on beam deflection, especially if something approximating a coaxial feed was going to obscure the weld pool. This led me to introduce a fourth axis along with the means to level the substrate, meaning that if the first plan didn't work out, at least I had a backup. As to what that plan entailed, it would simply be what had worked in the past, a two laser scheme which would see the wire being fed into the dead zone, but this time with the ability to maintain a consistent delivery. I had repurposed a viscous clutch taken from an Isuzu TD27, with the substrates being cut to size and the plastic components acting as placeholders until the steel components arrived. If there was one thing that stood out to me, it was that leveling was going to be an ongoing nuisance, and heavily compounded by an unconstrained bed. but that just seemed par for the course. Since I now had a rotating platform, I couldn't help but wonder what this process could achieve in an ideal scenario, that being an uninterrupted deposition relying on 2 lasers rather than 3. Now I did try 3 lasers momentarily, but without a coaxial feed that went about as expected, but with 2 lasers however, the reflections were much easier to manage. After the obligatory printing of segments, checking that I could translate a Cartesian scale to a rotational one, I tried putting down a few rings to gain a better sense of the deposition height. The unfortunate thing about this design is that the layer height and respective track profile are influenced by the energy density, with the energy density itself being partially defined by the laser overlap and relative angle to the translation path, amongst other things. I would keep the beams partially overlapped to create a high point to aid beam deflection, and would also keep the wire fed at 45 degrees relative to the path of motion for the sake of simple geometric tests. But even so, this wasn't immune to reflections due to corners and other disruptions which would then build on themselves. Furthermore, if the platform wasn't exactly level, the degree of overlap would change and so too would the deposition height. But on average, with a level platform and a velocity of 10mm per second, a track width of 0.8mm and a wire feed rate of 22mm per second, this would yield a layer height of approximately 0.14mm. Naturally, what would follow would be several tests to see how the layers stacked up, and what you're looking at here is the result of 7 layers which should have amounted to nearly 1mm. Instead, the height was only 0.85mm and the source of it I wasn't too sure of. It could have been that my layer height increments needed to change, or it could have been that the accumulation of heat was broadening the profile, creating a sagging effect. Either way, it wasn't good news. I was reluctant to start changing parameters at this point as I had already blown a couple of fibres, each time costing me a couple of days and several centimetres in fibre length. So at this stage I started to focus on the camera to gain a clearer picture of what was happening. This is just an example, but you can see the effect of not having the layer height balanced with the feed rate, causing the focus to retract towards the beam waist. Although this example happened much later on, it's likely that the rings were subject to the same issue, but this was at least a month later and I'd begun to question the merit of a 4th axis, at least in this format. Treating the red lines as the deposition path, you can see how inefficient this is, having to constantly realign the head with the platform to maintain a constant delivery angle, but this was a sacrifice I deemed worthwhile at the time. The major problem with this rotating platform was that if the head didn't exactly reference the center point, any misalignment would manifest across the build plate, leading to disjoint paths and asymmetries. There was an easy answer to this, at least on paper, which was to rotate the head, but as you can see there was a lot of mass and cables to move around, restricting the potential movement. I decided that I would try and simplify the design by reducing the laser count to 2, introducing a proper coaxial feed, and sacrificing the camera's overhead view if it enabled me to avoid complex path planning. This scheme would aim to keep the beams positioned 45 degrees away from the direction of motion, once again encouraging the reflections to bounce away based on a positive displacement. There were edge cases such as tight bends and 90-degree corners which had the potential to cause problems, but since I had now upgraded the lasers to 2 370-watt modules, I intended to control each module independently. The coaxial feed also made use of an XY stage as aligning the wire had proven to be exhausting, taking a disproportionate amount of time to get set up due to its delicate nature. Any slight bends upstream could also amount to a false alignment, leading to the wire missing its target and creating back pressure, creating a mess at the wire feeder. I wanted to solve this by reducing the distance between the outlet of the nozzle and the substrate. Copper nozzles had worked okay so far as they reflect most light at 915 nanometers, but I couldn't find any with a fine enough bore and therefore would still have to sleeve them with syringes. Reflections would still see the feedstock bonding to the nozzle however, and to try and get around this I would use a fibre optic ferrule made from an inert material, in this case zirconia. Pure zirconia unfortunately undergoes a phase change at roughly 1200 degrees centigrade and is prone to cracking as a result. I had to know if this would absorb or reflect laser light and to find out whether it could even handle the heat. The first thing I did was to expose it to the flame of a propane torch, and it did swell quite a lot, but never cracked. I also focused a laser on it, exposing it to the maximum power. It seemed fairly transparent to the beam, so I fed some wire through it and tested it again. And that did not go well. I figured I might be able to sleeve it with a copper syringe if I could find one, and tested it again while observing how the lasers interacted with the weld pool. That also did not go well. In fact, from what I observed during these trials, I came to the conclusion that this whole concept might not be worth pursuing. Even though this run illustrates the weld pool with 3 beams applied, you can see how the reflections are heavily influenced by the flow of heat, leading the reflections to follow in the direction of motion. This really steers the process towards needing a higher volume of material to help keep the reflections away from the feedstock, and that was a compromise I was unwilling to make. To keep the print seamless, I had favoured a finer wire and therefore a lower volume of material, intended to be offset by a faster print speed. But this created a lot of issues as it was particularly susceptible to reflections, which meant initiating the weld was a delicate balance between too much or too little. By this stage, I was implementing a method to rapidly advance the wire when the continuity between itself and the substrate broke. But luck would strike again, and this time it was the final straw. I'd had enough. At this stage, the head still needed to be redesigned to integrate a wire feeder. The substrates were also warping due to stress, and I was spending most of my time repairing the machine, sometimes getting less than one run out of it. I can't help but think that with the diode arrays, life was a lot simpler due to their ability to handle reflections, but the delicate nature of fibre-coupled diode pumps had really put me at odds with myself. They have the power, they have a small form factor, and are only getting cheaper, but at this scale and having to cater for all of the edge cases, I just don't think they're worth the time. Alright, so that was a very much abbreviated version of events, but it was kind of necessary to help bridge the gap. So while I was struggling with that, I'd been thinking about what had shown promise in the past, and now that I'd given up on all things DED related, I decided to turn my attention back to SLM. So I guess the best place to start is where things left off, and this picture pretty much sums up why I gave up on laser powder bed fusion the first time around. I was under the impression that the vacancy in powder running alongside the deposited tracks was due to recoil pressure. This is a pretty well known phenomenon, often resulting in denudation, where the recoil pressure creates negative pressure on either side of the melt pool, drawing the surrounding powder through the plasma stream. This appears to be a common enough problem in SLM, and as a couple of commenters suggested, a pressurized atmosphere seems to be the answer. But I really didn't like this, as this made the build substantially bigger, more complex and expensive. But I'd been thinking about it, and there was a major difference between mine and the more professional systems, and that was the power density. With a spot size of 300 micrometers, I could achieve a theoretical power density of approximately 2900 watts per millimeter squared. Plenty enough to create a cohesive bead, but far from the threshold of keyholing, which begins at around 10,000 watts per millimeter squared. Since my efforts were operating well outside the window where there would be enough back pressure to create a cavity beneath the plasma, I was a little unsure of why I was seeing what I was seeing. At 300 micrometers, the spot size is anywhere between 14 to 36 times that of a professional system, so it didn't have the intensity, but it had the volume. Now, since I was using a diode pump, I had around 200 watts of power on tap, but what I lacked was the fidelity of a fibre or YAG laser, meaning that I couldn't focus the laser as tightly as many professional systems can, at least not without a large degree of stray light. So I'd figured that if I could bring the spot size down to 50 to 80 micrometers, with a similar power density, I could get away without a pressurized atmosphere. And it would turn out that I was right, but for the wrong reasons, but I'm going to explain why a little further down the track. After how things had gone with the DED efforts, I wasn't super enthusiastic about starting from scratch. After all, this was just another theory. So I blew the dust off my old proof of concept and decided that this was going to be my starting point, but it needed a few upgrades first. Previously, I had just used a wood hole saw to provide a friction fit for the substrates, and this was fine as it wasn't under any serious thermal load and saw pretty limited use. But going forward, this wouldn't be the case, and I would replace it with, well, another hole saw. This received a bit of a trim and a tidy up, along with some hacksmithing that would see it fit for purpose. But this in of itself wouldn't be enough to cope with the heat, and since it was surrounded by PLA, I needed to get rid of as much heat as I possibly could. So I fashioned up a little water-cooled heatsink made from a herb grinder, drilling a couple of holes for some barb fittings and bringing it all together with some 2-part epoxy. I wasn't 100% convinced that this would be watertight, or whether the epoxy would even tolerate the prolonged exposure to water, but it seemed to hold up and has done so ever since. With everything pieced together, I would tactfully modify the powder bed to accept some water lines, along with the wiring for the thermocouples. Aside from these changes, the powder bed remained largely unchanged from my previous video on it. The biggest change, however, was the laser, and although I settled for this Nd:YAG arrangement, it wasn't my first choice. Ideally, I would have liked to have used a 50-watt ytterbium-based laser, as these end-pump systems offer much better m-squared values. This basically translates to how closely the beam resembles a Gaussian profile, and in turn how tightly it can be focused. The closer to one, the better. The major feature that pushed me away from these, however, is the integrated Q switch. This is a great feature for allowing the laser to achieve much higher peak intensities, which is perfect for ablating metals. But in the context of fusing metal powders together, depending on the characteristics of the powder itself, my impression was that this would vaporize the powder to be formed into a solid, and potentially disrupt the surrounding powder. There may be a solution to this, which is to simply unplug the Q switch, perhaps needing a dummy load to fool the electronics. But I was unsure of how the device would actually respond and conscious that it might just result in some expensive magic smoke, so I went for an alternative. These side-pumped ND-YAG lasers are a much older design compared to their fibre counterparts, but were once the upmarket tool for laser engraving. In fact, these are so old it was difficult to find any pictures of them in their natural habitat, almost as if they predate the internet. There is one company, however, with a befitting website still dealing with them. I'll leave you to guess what era they're from. They are still in production today and can be found secondhand on eBay or brand new on AliExpress, but beware that they are often sold secondhand for a reason, as I would find out. Much like the illustrations, the information available to the budding practitioner is pretty thin on the ground, leaving a rookie like myself to get tangled up in the theory chasing nanometers where millimeters will suffice. For those looking to cut their teeth, Leibold released a really good primer in the late 90s to go alongside their educational kit, explaining the general theory of the operating principles. I'll leave a link in the description. For most of these modules, the layout is the same, consisting of the module itself, a high reflectance mirror, an output coupler, and a beam expander. These combine to form a resonant cavity with the type and spacing of the mirrors dictating its style and characteristics. I would opt for a hemispherical resonator as this is the most commonly adopted format for the lasers in this power band. In terms of spacing and what mirrors to use, initially I couldn't find much in the way of worked examples, but I did eventually find this paper which noted the use of a high reflectance mirror with a radius of curvature of 800mm and a cavity length of 300mm. I would use this as the basis for my first configuration, but quickly discovered the limitations of the cheaper mirrors I had bought, damaging the mirrors at around 20 watts. The original mirror mounts I purchased came with a set of mirrors from a factory system, but unfortunately I had no idea of their specs. Even now I can only speculate based on what I have read, but suspect that the flat plane mirror is an 80-20 split, and the HR mirror has a radius of curvature somewhere between 1 to 2 meters. Gleaning information from sellers, it seems like 400mm is the typical cavity length, and switching over to new mirrors would bring the power up to just shy of 40 watts. The particular pump I'm using is a GTPC-75S, which as you may have guessed is rated at 75 watts, but this is rated at a rather awkward 29 amps whereas I could only provide 24, the max an RD series buck converter can supply. Even so, this should still produce 62 watts, but with the unit plateauing at 38 watts it was evident that there was something wrong. The power meter I would use to dial in the laser is just a cheaper unit, but it gives real-time feedback which is nice to have while making subtle adjustments to the mirrors. As I would power the laser up, I would see a brief spike to around 50 watts, with the power settling to below 40 watts. Unsure of whether it was just the meter stabilising or whether it was the power rolling back due to overheating, my initial suspicion was that there was a blockage within the pump, and I would test the flow, finding it to be above average. I would then spend more time than I would like to admit second-guessing myself, wondering how selective I actually needed to be with the alignment. Until eventually I would tear down the pump and sure enough there would be 2 blockages, but fortunately no dead diodes. With everything reassembled I could now pull 58 watts from it, which I was happy with, but there was still the issue of transverse modes. Since this is a side pump laser, the gain medium is much shorter than that of a fibre laser, and to achieve the same order of power requires a much larger cross section. This unfortunately increases the possibility of resonant modes on axes other than the optical axis, meaning that the output beam is composed of a series of rays rather than a single fundamental mode. This results in a multimodal beam, lessening its ability to form a tight focus, leaving the spot size compromised, which of course lowers the power density, print speed, and increases the feature size. I would measure the m² value at 3.91, a slight improvement on that mentioned in Leon's size paper. However, the spot size I would measure would be near 100 micrometers at 27% of its rated power, and would peak at 140 to 150 micrometers above 34%, suggesting that the m² value was actually higher. Since the refractive index of the gain medium changes with temperature, this could be due to the cavity being optimized at too low a power, but was likely the result of many things, from the cavity not being aligned well enough to the choice of mirrors in relation to the cavity length. Despite this, the figures quoted in Leon's size paper suggested it was performing reasonably well for a system without a mode selection element, and I would have to cut my losses here as I had invested quite a bit of time to get to this point. But at least now it could achieve a power density on par with the previously used diode pump, and open the door to using galvanometers. Operating at a more conventional wavelength with a better quality beam meant that I could avoid the hassle of supporting an XY stage, brought about by the poor structural support of a plastic container. The scan head I decided to use is the RC1001, probably the cheapest out there at around $170 to $220. This makes use of an f-theta lens to provide a flat focusing field with a linear scan angle, bringing the total up to around $280. To drive the scan head, I used an open source library called Opal, listed with warnings, making use of a Teensy 4.0. This converts a serial input stream into the XY2-100 protocol, bit banging values across the ports to support a 2 MHz clock rate. I ended up modifying it so that I could facilitate the basic features of the printer, controlling the power supplies, fan controller, and providing closed-loop feedback for the build piston. I originally implemented a motion controller alongside a quadrature encoder on an FPGA, with the intention of migrating the rest of the features across in time. But I quickly discovered that the water chiller I had purchased has a hidden feature, delivering multi-amp spikes which would end up damaging the FPGA. I suspect a lot of this has to do with the lack of buffering on the FPGA dev board and my chaotic wiring scheme. But even with the chiller placed further away, it wouldn't play nice and had to be put in the corner for timeout. In the end, practically all of the low-level tasks were carried out on the Teensy, with the FPGA hanging around as an interface for manual control and as a digital readout for the linear encoder. Moving forward, one of the first stumbling blocks in getting this off the ground involves setting the correct distance between the f-theta lens and the powder bed. Because I wasn't using an established control card, I couldn't simply reference the size of a projected image, and therefore made a tool which would sit flush with the powder bed. I didn't really have much luck with this, and I suspect this came down to several factors, the flimsy nature of the plastic container and my inability to load it correctly while adjusting the height being at the fore of them. I also tried projecting an image down onto the powder bed, but this didn't yield the result I was looking for either, potentially for the same reasons as before and the differences in wavelength. In fact, it would be a slightly more unorthodox method which involved using a thin piece of graphite, adjusting the height of the build piston until the surface began to oxidize, making corrections based on the difference, and dialing the power down as far as it could go to ensure the spacing was optimal. Other than ensuring that the powder bed and the galvanometer were in reasonable alignment, using whatever means I could, the next step was the inescapable printing of metal tracks. At this point, I'd already taken a couple of swings at it, but these all concerned the aforementioned problems. Going ahead, the next run would deliver more bad news, but this is where I started to uncover where things had gone wrong the first time around. And as for what had gone wrong, I had applied far too much powder for my first layer. And as to why, if memory serves me correctly, I'd had a lot of trouble trying to get the powder to cleave effectively, even going to the length of sanding the substrate to stop the powder from sliding over it. Eventually I just accepted that the first layer would be higher than the following layers, turning the laser up to 11 and calling it done. But unwittingly, I'd already solved this issue with the use of a plastic swipe card, but not until I found myself constrained for power would I have to reconsider this. So with the first powder layer now semi-transparent, I could produce cohesive tracks up to around 200mm per second, and noticeably without the vacancy in powder running alongside the deposited material. I had my guesses about why this was, but didn't feel that my theory regarding volume explained it, as the vacancy was wider than the track itself, but the answer would be revealed to me in time. My next move was to embark on the second dimension, taking the print speeds that had yielded nicely formed tracks and testing them against the different hatch spacings. I began with a series of tests with hatch spacings ranging from 25 to 150 micrometers, all conducted at a conservative 90mm per second and just following a typical zigzag pattern. At hatch spacings of 150 to 100 micrometers, the irregularities were pretty apparent, but not unexpected. They did help identify the effect of powder disturbance in comparison to the individual tracks though. At 25 micrometers, the irregularities remained but in a different format, seeming to embed the spatter from the previously processed tracks. I decided to push ahead and start stacking layers as the consequences of each spacing wouldn't really be known until given a chance to materialize. I only managed around half a dozen layers as the build piston would break free, but still managed to observe the settling of each scan pattern. At 150 micrometers, the individual tracks appeared more cohesive, blending together to form a tight lattice but suffering from a light amount of unevenness and spatter. The following hatch spacing started to resemble a skin, but with a higher degree of unevenness from embedded spatter, presumably due to overheating. You can see as the hatch spacing decreases, the individual striations lose their form, probably due to the excessive reprocessing of the material. Something else that was apparent was the formation of raised edges. I'd encountered these long ago, but at the time suspected they were due to excessive heat from a limited processing speed. I needed to find a way around this, as this would disrupt the print sequence as it had done in the past. Part of the appeal of switching over to galvanometers is the ability to experiment with different scan patterns, and something I had wanted to observe was the effect of multipass scanning. I already knew from driving the process at 90mm per second I was expending far too much energy, causing an excessive droplet size. I had hoped that by driving the process at a much faster speed, I could iteratively sinter the metal until it had completely fused, avoiding the creation of spatter. What I discovered was that the process speed I had arbitrarily chosen was too fast, and instead blew the majority of powder out of the area to be sintered. Even though it was a failure, it came along with a couple of revelations. The first was that the existence of the walls proved that the processing speeds of the adjoining segments were different to what I had programmed, bound by the processing capacity of the software. The second revelation relates to the very issue I mentioned in the beginning. The causation of the vacancy of powder running alongside the tracks likely had less to do with denudation and more to do with a poorly focused beam. I suspect there was a high enough degree of stray light which led to the adjacent powder being heated enough to create the surrounding gas to rapidly expand, blowing the powder away and through the plasma stream. Since the power was significantly higher to adapt to a thicker first layer, this likely worsened the effect, and without the tools to effectively measure the degree of stray light, it totally escaped me. I think denudation still plays a role in this, but to what extent I'm not sure. I would like to think that if I revisited that approach, I would come out better off second time around. After witnessing the creation of the edges from the adjoining segments, I decided that I'd rework the post-processing script so they would no longer exist. I also modified the script so that it would only generate a unidirectional scan pattern, simply to avoid horseshoeing, attempting to generate a more uniform heating strategy. Areas where the path for heat would be constrained would still suffer, but that was in the too hard basket for now. The first cube took around 4 attempts before I actually succeeded, mainly owing to the issues I mentioned previously involving the water chiller interfering with the FPGA. It wasn't much to look at and there was a clear amount of porosity, but it was a milestone complete. I also tried printing some overhangs using the same parameters to figure out what the limitations of this setup were, and as you can see, I was still battling with the system crashing multiple times per run. It seemed happy at 50 degrees away from the build plate, but at 40 and especially 30 degrees, it was reaching its limits. I was also witnessing my powder bed begin to break apart as using a hammer to level the substrate had taken its toll. I would persist with it for a little while as initially it wasn't too bad, and it would be a nasty job to deal with while I was already busy playing whack-a-mole with the other gremlins. I would come back to it later though. The plastic edge of the recoater blade was also suffering as the printed surfaces were eating away at it during every pass. This design would hang around for a bit longer than I would have liked, but was easy enough to replace even if it did slightly compromise the layer height. Problems aside, I set up another run to see if I could improve the surface finish. For this run I performed 4 tests with wall speeds of 190, 280, 370 and 450mm per second, a fixed infill speed of 280mm per second, and various hatch spacings ranging from 50 to 125 micrometers. I also decreased the inset of the infill from 0 to 50 micrometers, just to ensure no overlap would contribute to raised walls. It's pretty clear that of the 4 cubes, the surface finish was the best on the cube that was printed with the fastest walls and the shortest hatch spacing, with the appearance gradually degrading at slower speeds and broader spacings. You'll notice that 2 of the cubes are partially detached, and this was simply because I didn't repair the damaged recoater blade, and instead tried to position the cubes to avoid the damaged section. For a first attempt at improving the appearance, I was pretty happy with it. Unfortunately, the success would be short-lived. I followed this up with a few more tests, mainly driven by the curiosity of what faster speeds could yield. The next run would consist of 5 cubes ranging from 400 to 800mm per second, with wall speeds the same and a hatch spacing of 75 micrometers. Before I could get them in front of a sandblaster, immediately it was apparent that a lacquer fusion would see these settings as not much more than a candidate for support material. And with my very formal method of testing, not one of them would survive. I tried again, but this time performed a multi-pass scan attempting to eliminate most of the spatter by performing a sintering step followed by a melting step. Watching the footage I couldn't see much in the way of spatter, which was a win, but it appeared that the unevenness still remained. The additional heat from the multi-pass approach was also having an adverse effect on the recoater blade, particularly for the cubes aligned in a row, hence why they are shaped like loaves of bread. This would no doubt compromise the results, but at least one of them managed to survive me wrenching on it. Again, another series of tests, but this time at much more conservative speeds. These would result in stunted cubes after running short on powder. They did yield much better strength, but as you can see they are rather crooked due to the powder bed failing. I had to stop and address this before going any further, as this was no doubt impacting the focus of the laser, along with the geometry of the test prints. I had originally designed the powder bed with the intention of using very simple materials, keeping the price of the powder bed down to a few $100s. Where I'd gone wrong is using general purpose glue, which didn't take kindly to being hammered upon. It just so happened that the 2-part epoxy I use for bonding fibres also happens to bond metal to plastic, and supposedly is apt at dealing with impacts. I'd make an effort to scuff up the edges a little better the second time around, and after a generous application of glue, would have everything reassembled and ready for the next problem. Before we continue on, I think it might be worth making an aside here, because if you think I've been freewheeling numbers, you'd be right. Well, actually that's not quite the truth. There is a fairly simple concept called volumetric laser energy density, which is used as an index for performance. It's said to influence everything from surface finish to microstructure, and the formula is composed of the applied energy, scan speed, hatch spacing, and layer thickness, giving the applied energy per unit volume. The problem is these numbers can vary wildly depending on the system itself, as the applied energy is not the same as the amount absorbed, and that can be influenced by factors such as spot size and the behaviour of the melt pool. For 316 stainless steel, the numbers are commonly in the band of 50 to 80 joules per millimetre cubed, but this is assuming that the processing conditions are on par with that of a commercial machine. As I can't concentrate my laser as well, things would stray towards the experimental, and with that we continue forward. The next few runs would focus on dialing in the settings, as a lack of fusion was still undermining part strength. The most obvious answer to this was to increase the input energy, and seeking to minimise the potential for spatter, I would do so by reducing the hatch spacing. I dropped the hatch spacing down to 50 micrometers and started to search for a print speed that would grant me enough part strength without compromising too much elsewhere. This test yielded some okayish results, only just surviving me swinging on it, but it was apparent that it hadn't fully fused. The following test saw the speeds drop down to 120, 140 and 160 mm per second, and these cubes definitely showed signs of improvement, but you can still see the metal is softer than it ought to be, and I would confirm this using a hole punch. The reason for this is that the part density was only 78%, and despite trying to improve it would never surpass 84%. This is an area I am still working on and suspect there may be a few contributing factors. It won't be until the next video that I really address it though. Some other peculiarities would manifest as the prints would reveal themselves to be sensitive to orientation. I initially thought this may have something to do with airflow, but this didn't really make sense, as the height of the pinched edges was too consistent. The actual source of it would simply come down to the angular edges having an increased cutting effect on the recoater blade. I ended up replacing it with a rounded edge made from a harder wearing material, that being PTFE tubing. Unfortunately, I only had a smaller size on hand, but it would still address the problem whilst also slightly improving the part density. I also tried reprinting the overhangs, and these yielded pretty much the same results, but with far less interference from process failure. The final thing I wanted to print before calling it a day was a benchy. The print volume is very limited, as this is very much a proof of concept, but it could still handle a benchy at 50% scale. It would take 5 attempts before succeeding, with the first failing due to there still being some undiscovered issues with my controller, leading to a double application of powder, causing a lack of fusion and some areas to just crumble away. The second benchy would fail due to me underestimating how much powder was in the hopper, and the third would fail with me realising the step size was also responsible for the shortage of powder. The fourth benchy would fail at the 11th hour due to the build piston breaking free, and finally, the fifth benchy would allow me to call it done. The final print took around 2 hours and 12 minutes, consumed 132 litres of argon, and achieved a final density of 78.9%. There's obviously a lot of room for improvement, and I'll be shooting for near full density in my next video, attempting some more unconventional things too. But this unfortunately means this particular powder bed design will be going in for another round, while I focus on other things. I have been working on another design, and it will be quite a significant departure from this build, but all in due course. Anyway, that's where this video concludes. If you'd like to support the effort, you can do so however you please, but otherwise I'll see you in the next one.